let's go for it.
Hello everyone. My topic is educational FPGA platform with open source toolchains and Ibingu. Uh, I was an undergraduate student from the University of Science and Technology of China, and now I'm a PhD candidate at the University of Tokyo. I'm an amateur FPGA programmer. I've been doing things like RISC-V and PCB design, also some Zinc work. I've been visiting maker fairs, and these are some boards I made, including a 6-layer CU15EG and also a 2-layer Zinc 7000 with BGA. And I've also been working on some no-MMU RISC-V Linux things. About today, I'll be talking about first open source FPGA toolchains, then my experience as a student in those educational courses, and then the online platform we have been developing. First, about the open source FPGA toolchains, it's been about 10 years since the first toolchain, the Ice Storm, was invented for lattice SE40, and at that time it supports the very small FPGA family of SE40 with only up to 8K logic elements. Then there came ECP5, and there are Gowin, which supports this Gowin family. They have a cheap price and up to maybe 20K logic elements. And for the most widely used Xilinx 7 series FPGAs, previously there were F4 PGA, which supports the RTX family having up to 200,000 logic elements. Then around 2 or 3 years ago, there came OpenXT7, which supports a larger Kingtech 7 family. So there's already 500,000 logic elements. The story might be 2 or 3 years ago, there came some very cheap boards like this one from QM Tech. They are with this Kingtech 7 7K325T, but this requires a very expensive license to use. So open source people just came up their own way with this open source toolchain. And of course, the official toolchain is the canonical way of development, but now the open source toolchain can already do a lot of things. It supports designs like Pico RB32. They are open source DDR3 controllers. This Uber DDR3 by Angelo Jacobo. There are some different kinds of RISC-V softcores. There are SD cards and HDMI drivers, also IO30s. It supports Spartan 7, Arctic 7, Kingtech 7, the Zinc series, as well as some high-speed transceivers like PCIe endpoint on Arctic 7. And about more complex designs like SATA controller or 10 gigabyte Ethernet, or like PCIe root complex, I know there are people working on it, but today probably it's not working on open source toolchains yet. And one advantage is it runs on ARM machines. So on Apple's M1 computer, there's no Vivado to use, but there's that open source toolchain. And it also runs in Docker, so it makes it very convenient to run on various platforms. You can just pull the Docker container without installing anything locally. One example to show how flexible this is on a Zinc 7000 SoC. Zincs are a kind of special FPGAs with a ARM cores tied together with the FPGA fabric. So for ordinary FPGA, it's good at custom logic, but if there's a lot of sequential commands to execute, then we'll need to instantiate a soft core. This is a waste of logic elements and energy. So Xilinx just put some existing processing power onto this FPGA, and this is very popular among embedded devices. And with the open source toolchain, we can laterally run Linux and OpenXT7 on the ARM part and let it generate its own bit stream on this only 1 gigabyte of memory. And this is laterally impossible with traditional FPGA development flows. And for the Zinc ARM part, it requires some extra configuration. If you have used it, you know that building the firmware is kind of painful. but now we also have this Gen Z to generate those PS configuration parameters, and it will give you a full command line based flow. So no more Xilinx SDK, and you can have a boot firmware in like 5 minutes. And how about on the educational side? Like for undergraduate course like digital circuits, Xilinx and Altera FPGAs are widely used. Well, Altera don't have a FPGA toolchain right now, but for Xilinx, if we consider commonly used tasks like the beginning level blinky or like 7-segment displays or some buttons or switches, and then slightly advanced things like adders or an ALU or some clocking wizard, we play with the clock frequencies. And for more complex things, which may work as a more advanced course or like the last customized project for students, we have UART, maybe RISC-V. We may experiment with cache structures. We may use existing IPs for larger memories. And we can see actually FPGA, the open source FPGA toolchain is capable of all of these. And then what's my experience as a student? Well, the first thing is at that time, there's no idea about open source toolchains at all. The teachers are not teaching it, and I remember I was searching on Reddit, is there an open source toolchain for FPGA? And people said no, and it's impossible because blah, 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 blah. But now we know that it's no longer this case, and actually starting from open source toolchains might be a very good starting point. By taking into this course, I got some feedbacks from the friends and teaching assistants. For example, like setting up the environment is very hard, and compiling a very small design is slow. It takes like 3 or 4 minutes just to compile a Blinky. And for like students taking their very first digital course, this is very frustrating. And of course, the flow is very different from the Makefile based software flow. At that time, we were using this Nexus 4 DDR board with RTX 7 FPGA. This is a quite powerful device. But like at that time, we are using that heavy toolchain, and we feel, wow, this thing is hard to use. And the students are spending a lot of time without like making progress, just solving these very basic problems. And I believe, like even though there's no silver bullet, this open source toolchain will help a lot on bring students into these digital designs. And when we step forward to this computer organization and design course, which is 1 semester after, where students design their own RV32i RISC-V processor. And my observation is, first, that board is called Nexus 4 DDR just because it has DDR memory, but no one is using that because it's complex. We gotta click through that many pages of like MAG to get it work. So since there's no DDR, where can users have memories? SD card. Tuning SD card is very painful. For beginners, writing an SD card driver takes at least more than the course allows. So their only way left is the FPGA VRAM, and they synthesize RISC-V code, like their assembly, directly into block RAM. This is a very bad practice. They will like lose picture of the whole structure, and their code size is extremely limited. They cannot literally use any libraries because these are large, only because they have no access to memory. And of course, debugging is primitive. They have LEDs, they have 7 segments display to show one 32-bit integer, and probably that's it. There are not so many like useful debugging methods. Of course, like this VRAM can be read and written, and if during their processors running, if they want to inspect the content, there's just no way. Of course, you can write like a UART driver or some more advanced drivers, but that will quickly become even more complex than the design itself, and it's like a very big description. It's a very big distraction because in this course, students are focusing on the RISC-V core, and they don't have much experience. So this whole thing is making the progress very hard. So we came up with a online educational platform. The original reason is previously we are giving boards to students, one board per student, but then after some time, some boards will break, and replenishing these boards can be quite tedious, and the boards are expensive. And then there came COVID. So we were developing an online educational platform, and then we just applied it to these courses, and it feels, well, it's not bad. So for the first generation of platform, we were using the same board just connected to the Raspberry Pi. So previously we have some 40 boards to give to students, to the students joining the course. Now we just don't give them the boards, we just connect them to a Raspberry Pi and serve them in a server room. So students can access a website running on the Raspberry Pi and program this board just through this USB cable connected to the Raspberry Pi's USB port, and it has some GPIOs. But this function is rather limited because Raspberry Pi's I/O is slow. It's having difficulty pulling a few megahertz. And if you want like 3 URs, 5 URs, can the Raspberry Pi do it? That's kind of hard. So later we realized that to fully pull out the power of one FPGA, we're going to have another one for sampling. And meanwhile, we're going to host a web page and handle the bitstream programming. Then what's the solution? The solution is something with both processing power and FPGA. That's a Zinc. So we use a Zinc here as a system, and we connect the Zinc to a Artix FPGA, which the students are using. So on this self-made PCB is a quite integrated setup, and this board can be hosted in a very dense manner in the server room. And we have this kind of front end same as before. And for the structures, it's like this. The user FPGA have a DDR3, but the Zinc also have a DDR3. And most importantly, the IOs between, there are hundreds of them, and the speed can be very high. We can just run any kind of protocols by using the Zinc PL as a host and user's FPGA as a device. And by this way, the high-speed communication can happen. And if you want to debug some peripherals or whatever, we can just let user do it. And the user can upload a file into the Zinc's DDR3 memory, and then from Zinc's PL, the DDR3 can be accessed. And finally, from the user's FPGA, the user can access the DDR3 memory from the Zinc. So the result is user can upload a firmware from the website, and then our whole gateware will allow the user's FPGA to directly access it. This will eliminate all the complex problems happening before, because in the middle part we have I/O interfaces. This is customized, so we can make up any like very simple interface for communication. And this is just the beginning. Like this setup can potentially handle much more than an undergraduate course. It can monitor the memory, the Zinc's memory real time, can take like memory snapshots. It can capture the waveform, like capturing all the IOs going into the FPGA. You can use the PL or the user FPGA as a simulation accelerator or whatever. And if you have like one on the Zinc, one on the FPGA, you're going to have a communication of whatever protocol you are verifying. And this is a teamwork with Professor Jianliang Lu. So if you have any question or interest about this platform, you may contact him via the email. Now let's have a demo, and it's free to use for everyone, so you can also you use it on your own computer. So you're gonna click this visitor login. For like visitors, this is still open, and you can acquire a node with a zinc. And then you can see the link here, and you can click it to see this platform. So on top there's a bitstream upload, and on the bottom there's a storage upload, which you can upload the memory for the, for example, RISC-V processor you're running. Like we can select some file. Like this memory with a Linux inside, and we click upload. Now this is finished, and you can see already this frame buffer display is just a map of the memory, so it will literally show what this firmware looks like in the memory. Then we're just gonna upload the bitstream to the Arctic 7. We can see that the RISC-V processor is loaded and the LED starts blinking. The boot ROM of the RISC-V core is being loaded and is printing some text into this terminal. On the text here is testing the memory and is laterally copying the memory from the Zinc DDR into the Arctic's DDR. And here for the DDR3 driver, we are also using the open source Uber DDR3 instead of the proprietary MIG from Vivado. Now we can see it's loaded and Linux has started booting. This is a 32-bit non-MMU Linux for RISC-V 32-bit. You can see here like the Linux is running and you can have some development. Of course, now we can only upload the shared storage. Later we may add the function of download this shared storage. So if something went wrong, users can easily inspect it. And well, where's the open source toolchain? Previously, I'm just demonstrating the platform, but actually we have another standalone website called Compiling as a Service, which is a full FPGA development flow in the browser, like it's hosted on this URL by Symbiotic EDA. Well, we all know like SAS are sometimes kind of annoying, but I think it will be okay if you can host whatever you want on a custom website. Like the front end and back end of this website is all open source at this place, and laterally you have a browser interface to interact with the code, and then you can submit the compilation onto the server, and the server will do the compilation by calling a Docker container containing all the tools. And I also show this. If you go to the website, then first you see editors for constraint files and Verilog source file. And on the bottom, there are some compilation log, and there's a web-based FPGA programmer. This is just Open FPGA loader ported to WASM. Like I have a simple board here, and we can select the example for it, the Microphase A7 Lite. This is also a RTX 700T, same as the Nexus 4 DDR we were using, and I can click submit to let the server do the compilation. And after like half a minute, it finished. We can of course download the bitstream to our local computer, but since my board is just here, we can use this web-based programmer. First, we're gonna connect this USB device and select like this is an FT232. We can run detect FPGA, and we can see this RTX 7 being detected. Then we just run this program bitstream, and the bitstream will be downloaded from the server and blast into this FPGA card. There are only 2 LEDs, so maybe it's slightly hard to see, but you can like literally do everything on this platform. And now we are improving these functions to have a simulation. This is still in work in progress, but in theory you can run the simulation and then somehow see the waveform in the browser. That's what we are planning to do. Now we can only like grab the log of this simulation, but I think it's a good starting point. Let's go back to this talk, and what will be the future? I believe freedom will be the future. Like now we already have open source IP cores for like Uber DDR3, like for Ethernet, and for most things that is hard to imagine maybe a few years ago. So in the future, maybe there will be cores for DDR4, there are cores for SATA, and I think it's not only just open source FPGA IP cores, it's the open source IP cores with the open source toolchain. A very good example will be this Open Wi-Fi or Pluto SDR firmware. These are all open source, but so far they are still only running on Xilinx FPGAs because they need Vivado, and the toolchain is not open source. If they can be ported to open source toolchains, then just like the Uber DDR3 is running on Lattice as well, this kind of awesome SDR projects will also be ported to more and more FPGAs, and I believe that will be the future. Yeah, at last, I would like to thank Symbiotic EDA, as well as the VLab and the Linux user group from the University of Science and Technology of China, also the Tokyo Linux user group, also the AONet Foundation and NGI Zero. And thank you very much. I'm very sorry that I couldn't come to the site myself. I hope to see you maybe on next Coscap in real life.